Okay, welcome to Psych 319, Chapter 4, Part 2. So let's talk about the stimulus for vision. Vision starts with light, and what light is um, visible light is a narrow band of the electromagnetic spectrum, and what that means is that all the energy in the universe is composed of some type of energy particle, quantum or whatever, that is moving through the world in generally a straight line, and it has a wave-like property. And we have evolved to be able to detect certain wave types in the universe. So for example, we can see wavelengths that fall within the visible light spectrum between 400 and 700 nanometers, but we can't see infrared or ultraviolet. Bees, for example, can see ultraviolet rays, but we cannot because it hasn't been very useful for us in our evolutionary history, so we didn't develop that ability. So light is a wave with wavelength and amplitude, and what wavelength is it's the peak-to-peak distance between waves. So if you think about, follow my mouse, if you think of a wave as traveling like this, the wavelength is the peak-to-peak distance between the tops of those two peaks of the waves. And it has an amplitude, so a small amplitude wave would look like this, and a large amplitude wave would look like that. So we separate the physical world from the perceptual world. In the physical world, we say that light has a wavelength and an amplitude. Wavelength being, again, that peak-to-peak distance between the wave crests, and the amplitude being the height of the wave. And in the perceptual world, those are transformed into hue and brightness. So when we think of color, what we're actually thinking of is hue. Hue is your perception of wavelength. This is our internal representation of wavelength. So when we say we see red, we are perceiving and interpreting a wavelength of 700 nanometers. And when we say we perceive a light as being bright or dim, what we are is actually perceiving differences in amplitude. So a low amplitude waveform is perceived as being dim, and a large amplitude waveform is perceived as being bright. So all perceived light varies in hue, brightness, and saturation, how rich or faded the color is. And that really has to do with how much white light you add to the pure color, and you could forget about that for now. So the anatomy of the visual system is quite complicated, but I'll bring it down to the simple points. When you get to the eye, there's all these complex mechanical apparatuses here that work together to allow you to see, but there's really one basic function here, and that's to focus light from the outside world onto your photoreceptors. So the cornea acts like a magnifying glass, the lens acts like a flexible magnifying glass, so this allows you to focus light to a point here, the fovea, and the fovea has a very rich concentration of photoreceptors, which are the cells that respond to light. And all of those photoreceptors send a signal down the optic nerve to your brain. Now there's one part of your eye, like I mentioned, where all those neurons send their signal, and because they're sending a bunch of fibers outside the eyeball, it turns out that we can't put any receptors at that one location. So here you have the fovea, and then here you have this hole in the eyeball where all the nerves leave. And because all the nerves are leaving through that hole, you can't put any photoreceptors there. So in actuality, we're really blind. We have a blind spot in the world that we can't see because we have no detectors. Now, you have two eyes, so the good news is one eye tends to cover for what the other eye can't see. But even if you cover your left eye, you still won't notice any hole in the visual world. I'm trying to get this solution to work while I'm talking at the same time. So let me make sure okay. So what you can do is you can stand about a normal viewing length from the screen. I want you to close your left eye and focus on this central cross target here. Now move back and forth until the gray spot on the right disappears. You have to be looking directly at the fixation cross and kind of move forward or backward very slowly. It's somewhere about 6 inches to a foot. You should see that gray circle totally disappear. Another way of doing that is by using the demo in your book. I believe there's also a very good demo there. So why don't we perceive this blind spot? Sorry if I ruined that illusion for you, but um, that blind spot is always there, but we don't perceive it. And the reason is our brain is constantly filling in the blind spot. The brain is taking the information that it can see, and it uses that information to interpolate and fill in for the information that it can't see. This is an example of top-down processing, and we'll get into that in a little bit. Now, here it is again. Perceptual filling in for blind spots indicates that perception is a top-down process. What does it mean by top-down? Well, before we talk about top-down, let's talk about bottom-up processing. So here we have two cubes, and you might look at the colors and say, well, these cubes are identical. You might also note the obvious, that there's yellow ambient light on the left and blue ambient light on the right. But what I'm going to tell you, you can verify for yourself using a piece of paper and poking two holes in it, that this color here, you perceive this as a yellow square. It's actually the same shade of gray as this blue one over here. These are actually both gray, this one here and that one here. But because the surrounding contextual information biases your perception, you perceive this one on the right as yellow and this one on the left as blue. The reason I'm calling this bottom-up processing is that even if I tell you this information, you still can't help but perceive the square on the left as blue and the square on the right as yellow, even though you know that they're both gray. And the reason is that the stimulus is very strongly influencing your perception of these colors. That information is flowing up from the bottom, from your retina, to the top, your brain. And no matter what you do, you can't do anything to influence that interpretation of information processing. This is the opposite of top-down processing. So some of you might recognize this figure, and some of you might not. It is composed of various vegetables and meats. So some people might see just a bunch of cucumbers and squashes and an eggplant all arranged. And some of you might actually see a famous figure from the movie Alien. So these fruits and vegetables, or mostly vegetables here, are arranged in a way to form a monster, where this is the teeth and this is the hand. You can see the arm here. It's probably not too hard for you to see this. But some people actually miss this because they're not familiar with the movie, and so this just looks like a bunch of fruits and vegetables to them. And this is an example of top-down processing. Your experience can bias your perception of a figure. So bottom-up processing goes from the stimulus to the brain, and top-down processing goes from the brain to the stimulus. Basically, we influence our perception of things by our experience. Now, the Gestaltists were psychologists, a group of psychologists in the early days of psychology, and they were very keen to how object perception worked, and they described a bunch of laws that sort of described how we organize things in perception. One way we do this is through proximity. Most of you probably see, when I ask you what you would see, you would probably say, I see 3 groups of red dots, rather than saying, oh, I see 12 red dots. No, you arrange them in groups because of proximity. They're located close to each other, and therefore you group them as such. What do you see here? Most of you probably don't see, I see, oh, what is that, 6 times 6, 36 dots. You probably say, I see, oh, 6 columns of dots. Well, why did you say columns and not rows? They're also arranged in rows. And as again, it's proximity. The closer things are together, the more we group them. And there are other types of laws like this, like closure. You might see this as a triangle, a face, and the letter E. Well, this is not actually a triangle because there's a gap at the top. But our brain fills that in, and we complete the triangle. This isn't a face, it's just a bunch of lines on the screen. It doesn't really look much like a face at all. But we use that information, and we fill in the blanks. And we complete whatever information we need to in order to make sense of the stimulus. All of this involves top-down processing. Again, the E is not closed, More examples. Similarity, we group things based on how similar the features are to each other. So you probably see an X down here because the circles look similar to each other. There's some grouping going on here. Continuity, you'll tend to see continuity in lines that could be interpreted as either continuous or abruptly shifting in direction. Here's an example of continuity in the subjective contour illusion. So many of you probably see blue squares hiding behind 4 holes in a white sheet of paper with 4 holes cut out of it. But the truth is there's actually no line continuing these whatsoever. Again here for the illusions down below. But we perceptually complete this line because we want it to make sense. Another interpretation of the stimulus is you could say, oh, I see a bunch of Pac-Man figures. But there's such a strong organizational influence to sort of want to complete continued lines. It makes sense rather than having 4 Pac-Man facing each other. It makes more sense to say that there is a square here that is part of the same figure. And this applies to complicated image processing as well. So here's an example of a famous person. And I want you to notice, well, what's wrong with the picture. Can you recognize who the person is? It's a little bit dated, but this is a picture of the former Prime Minister of Great Britain, Margaret Thatcher. And what you may have noticed is, yeah, there's some kind of funny lines going on here. There's clearly some cut and paste, but you could still recognize her if you knew who she was. I'm going to flip this image upside down. Now it looks quite grotesque, right? Even in the previous image, the eyes and mouth were flipped relative to the head. And it's not as noticeable in the upside-down image because we haven't evolved to need to see upside-down faces. However, we're very sensitive to seeing upright faces. And so any perturbation in a upright face we're very sensitive to. We can tell right away. It looks terrible. However, the way this works is we have just enough information in this figure here to say, oh, we see hair, we see eyes, we see mouth and nose. We glue that all together. The brain fills in what it doesn't understand, and it says, okay, I see a face, and that those features are consistent with Margaret Thatcher's face. So I'm going to say it's Margaret Thatcher, even though in the real world we know the perceptual stimulus is very different. So I'm going to get into these theories of how we recognize objects in the next slide, but that sort of hints about what's going on here.